Okay, so welcome to CSC 475, Artificial Intelligence. I've forgotten exactly what lecture this is number-wise, but we're going to be finishing up perceptrons today, and we're going to be moving into neural networks, multi-level neural networks. So the first thing we want to do is we wanted to recap just a little bit. We had been talking about the capabilities of a perceptron. We had been talking about what the decision surface of a perceptron looks like. And so we had talked about the fact that the perceptron learning algorithm can learn anything that a perceptron learning algorithm can teach a perceptron, anything a perceptron is able to understand, okay? But there are some problems that perceptrons are just not capable of understanding. And so mathematically, what you have is these problems are often called linearly separable problems. And the reason why they're called linearly separable problems is if you have a problem with exactly two inputs, right, you can plot those inputs as points on a 2D surface, right? And so if you've got two inputs, then you'll get two numbers. You can view one as x1 as the x-axis and x2 as the y-axis, just like we did last time. And so you can plot all of the points in your input space. And a perceptron can learn a problem if you can draw a straight line between the two classes. A perceptron only generates a 1 or a 0, so a perceptron can only separate between two classes. And so if you can draw a line between the two classes, then you can say, okay, the perceptron can learn this. And really all of the algorithm is doing is it's moving, as we'll see here in a few minutes, it's just moving the orientation of that line. Now, you can only plot points on a surface, right, when you only have two inputs, an x1 and an x2. What if you have fewer inputs? What if you only have one input? Well, then if you only have one input, if you think about your entire space, it's on a number line, right? You might have an input of 25, or you might have an input of 50, or you might have an input of -10, right? So your inputs are just going to be numbers. Your decision surface in that case is not a line. Your decision surface is a single point. So anything, maybe your perceptron has learned that the cutoff point is, 23. So anything greater than 23 will be in one class, and anything less than 23 will be in another class. So what we've just done here is we've gone down a dimension. We've gotten one input, right? If you've got one input, then your decision surface is a single point, right? And if you can separate your inputs by a single point where one class is everything bigger than that and the other class is everything less than that, then that is the kind of a problem that a one-input perceptron can learn. If you have two inputs, again, you can plot your all of the inputs in on a two-dimensional grid, and if you can draw a straight line between those two classes, then that's linearly separable. That's a learnable problem. If you have three inputs, an x1, an x2, and an x3, well, then you can plot all of your points in a three-dimensional space. And if you can separate the two classes by a plane of some sort, then that's a perceptron learnable problem. If you get four inputs or more, well, I can't tell you what it looks like. For four inputs, I can tell you that if you could plot in four physical dimensions, your decision surface would be a cube, and everything in one to be within that cube, and everything in the other class would have to be outside that cube. But you're plotting things in a four-dimensional space in that situation, and I can't draw that for you because my brain isn't built that way. So one of the things is Um, I'm sorry, I'm seeing questions that have nothing to do with the lecture content, and that's causing me confusion. If you've got questions that don't have to do directly with what we're talking about, if you could hold those to afterwards, that would be great. Thank you. So where was I? So yeah, for simple 1, 2, and 3-dimensional problems, the human brain is fantastic at being able to just look at the problem and tell you whether it's perceptron learnable. For more than 3 inputs, the human brain doesn't really help. We're not wired to be able to understand problems in of dimensionality greater than 3 physical dimensions, and so our brains can't help us there. We can still understand these decision surfaces mathematically, but we won't be able to visualize it in our head. So one of the things about perceptrons that really sort of killed the field for, oh gosh, 20 years or more, was the discovery that some very simple problems were not solvable by a perceptron. Let me show you one very simple problem. I'll show you 2 very simple problems that are not perceptron learnable. Here you have a situation where we have where we have 2 problems that are not perceptron learnable. These are 2 input problems. There's one here on the left and one here on the right, but one input would be x1 and one input would be x2. So just like we've been playing with earlier, a perceptron with 2 inputs. It is impossible to solve the XOR problem, the exclusive OR problem, using a perceptron. What does that mean? A perceptron cannot learn, a 2-input perceptron cannot learn the XOR function. Now, why not? Why can't it learn the XOR function? Well, what is XOR? XOR says either one or the other, but not both. So this captures it. Let's say you have an XOR and you have both inputs are 0. Only output's 0, right? Neither of them are true. But if you had 1, 0, this point represents a 1 for x1 and a 0 for x2. So this is 1, 0. XOR should say yes, because it's either, but not both, right? So this 1, 0 is true on an XOR, and 0, 1 is also true. And because in this case the x2 is lit up, but the x2 has a 1 in it, but the x1 has a 0 in it. And in this one, the x1 has a 1 in it, but the x2 has a 0 in it, right? So these are the 2 XORs. And what about this guy up here? Well, this is where both x1 and x2 are both 1. Well, that has to be turned off, because in an exclusive OR, it's either, but not both. Okay, so these 2 points have to be in one class, on class, the generate a 1 class, and these 2 points have to be in the don't generate a 1, generate a 0 class. And we've got a little decision surface, which will be a line here, and we've got to move that line to get all of the gray points on one side and all of the yellow points on the other side. And there is no line. I mean, you could draw a line here, and this guy would be a 1, but this guy would be off. Or maybe you could draw a line here, right? Well, but then this guy would be on, because he would be on the same side as these 2. So there is no line that you can draw to separate the 2 inputs that need to be on from the two outputs that need to be off. The two input pairs that need to be on versus the two input pairs that need to be off. 0, 0, you need to be off. 1, 1, you need to be off. 1, 0, you need to be on. 0, 1, you need to be on. There's no way you can learn an XOR. And so that's bad. But really, sometimes everybody always talks about the XOR problem, and that's great. But there's actually a better, more intuitive example to use, and that's equal. Okay, equal. XOR just means not equal. We don't call it that, but that's what it means. It means the two inputs are not equal. 0, 0 is equal. 1, 1 is equal. XOR is when the inputs are not the same, when they're not equal. So 1, 0 or 0, 1. Right? But you can rephrase this question and say, well, can an XOR tell if its two inputs are equal? And it can't, because now you've got 0, 0 and 1, 1 that are supposed to be in the yes, they're equal class, and 0, 1 and 1, 0, sorry, 1, 0 and 0, 1 are in the no, they're not equal class. And it's the same problem. I've just swapped what's on and what's off. There's no line you can draw to separate the two yellow dots from the two gray dots. So a two-input perceptron can't even learn if its inputs are the same or different. And that's why perceptrons died for about 20 years. Once you tell somebody that, well, yeah, we've got an algorithm that'll teach perceptrons things, but the algorithm can only teach a perceptron what it's capable of learning, obviously. Okay, well, are there any restrictions on what a perceptron can learn? Well, there are a few. It can't tell if two inputs are equal or they're not equal. It's like, duh. Okay, well, this is useless. And that's really the core reason why perceptrons died as a research area for 20 years or so. Again, everybody, please remember to put those little mute buttons on. Okay. So, are there any questions about what I mean when I say linearly separable? Okay. Do you understand? Do you see clearly? A two-input perceptron can't tell whether its two inputs are equal. It can't tell whether its two inputs are different. So it has extremely constrained problems that it can learn. And you might say, well, add lots more inputs. That will solve the problem. You only need two inputs for OR, and, XOR, equal. It's not gonna work for that. Now Zachary just asked a really great question here. Would it not work to have a series of perceptrons? Exactly. It would work to have a series of perceptrons, but now you're talking about multiple levels, right, that have to be connected, that information has to flow through. And the perceptron learning rule could only teach single perceptrons, okay? And so people were stuck. They would go, okay, yeah, theoretically, Zachary's right. If you had a multi-layer perceptron, and I'm going to give you some examples of it and show you exactly how a multi-level one can solve the XOR problem here in a little while. But there was no learning rule to teach it. You would have to wire it up by hand. And so it was true, but it didn't really help you, was the problem. Okay. So again, I didn't see anybody type in any problems. So I guess that's good. There were no questions there. Now, one of the things that we talked about was initial weights and the values of those initial weights and the the value of the learning rate. And I told you that, I told you that you can use any weights to start with. You can set everything to 0. You can set everything to 100. And that the perceptron will still learn to categorize the problem given enough time. Now, I don't like for people to just take my word on things. So one of the things that I did, and you have this, you have posted to Moodle right now, you have the notes, and you also have a spreadsheet that I built. Let me bring up the spreadsheet. Here is a spreadsheet that implements a perceptron. Yes, you can build a Excel spreadsheet that implements a perceptron. Okay. And here is a spreadsheet that implements the little problem that we gave in class last time. It's the problem where you have the well, let me switch to the other screen so I can show you the problem again. This is the problem, not the eczema problem, but this is the little problem right here. It's kind of tiny, but this is the little problem that we've been playing with, right? Where you've got X1 and X2, you've got 2 inputs, but all of these guys need to be gray, and these guys need to be yellow. So it's exactly the same problem we've been playing with earlier. But now I've built a Excel spreadsheet that implements this problem. So, for example, if X1 is a 1 and X2 is a 1, then it's gray. It doesn't fire. If X1 is a 1 and X2 is a 2, it doesn't fire. It doesn't fire on 2-1 or 2-4. It does fire on 3-1 and 3-2. And if you go back and you look, or actually I don't have to go back. I can scroll down a little bit. And here is the problem. Now, Excel doesn't have pretty colors and crap like that when I'm trying to plot things, but here are the 2 points that it needs to fire on, and here are the points that it needs not fire on. And you'll remember our initial randomly chosen decision surface was just X2 equal 3. Well, if you look here, I've given the inputs, right? So these are all of the little inputs. I've given the desired output classification. These guys are in green, which means they're inputs here. I also used the learning rate of 0.22, and I used the initial weights that we had. Weight 0 was a -3. Our threshold value was to be a 3, so minus the threshold. Ignore the first input by having a weight 1 of 0, and everything will depend on the second input by having a weight 2 of 1. This is exactly the numbers that we went through last time. And if we scroll down, you can see, okay, for the first step, here's my decision surface. Here are the outputs that it guesses, right? The only one above the decision surface is this guy here at 2,4. So 2,4 will be the only one that generates a 1, right? That's the only one that will generate a 1 is this, the 4th input, right? And I give what inputs are supposed to be the correct inputs, and or actually this is asking, is the output correct? The output here is correct. It should not have fired. The output here is correct. It should not have fired. The output here is correct. It should not have fired. The output on the fourth input is a 1, but that is not correct, okay? It should not have fired. And the output of the last two are zeros. Is that correct? No, it's not correct, okay? So again, here are our 6 inputs. It's not supposed to fire on this one, this one, this one, this one. It is supposed to fire on this one and this one. The only one it fires on is the one above the decision surface, this one. So all I'm doing here is I'm going through the inputs that I have listed, 1, 1, 1, 2, 2, 1, 2, 4, 3, 1, and 3, 2, and I'm going through these 6 inputs in order, and I'm saying, is the first input, is its output, what is its output, and is that output correct? So 1, 1 should generate a 0. Is that correct? It does generate a 0. Is that correct? Yes, it is correct. So it's neither a false positive nor a false negative. The second one, which was, I think, 1, 2, is that one, it generates a 0. Should it have generated a 0? Yes, it's correct. So it's not a false positive or a false negative. The third one is also correct. So it doesn't generate a false positive or a false negative. The fourth one, again, the fourth one is 2, 4. That is the fourth input here, 2, 4. Okay. What does it generate? It generates a 1 because it's above the line. But should it have generated a 1? Is that correct? No, that's not correct. So it generated a 1. It shouldn't have. So it's a false positive. It generated a positive, but that was wrong. So it's a false positive. And the last two, which I think are what, 3, 1, and 3, 2, or something like that. Well, those generated no's. They did not fire on the initial decision surface. Again, what's the initial decision surface? It's just this straight line at x2 equals 3. So these two guys, it's supposed to fire on, right? But it didn't. And because of that, those are both false negatives because it generated a negative, but that negative is incorrect. It should have generated a 1. So it generated a 0 here and a 0 here. Are those correct? No, they're not correct. How is it a false negative or a false positive? It's a false positive in this case. Sorry. It's a false negative in this case. It generated a negative. That negative was incorrect. False negative. So then what's the next thing you're supposed to do in your little algorithm? Well, you're supposed to compute the sum of the false positives. There's only one false positive, so that's x1. So that's 1, 2, 4. There are 2 false negatives. You sum up the inputs. Where do those inputs come from? Well, they are these two guys, right? They're false negatives. And what are the numbers associated with them? 1, 3, 1 and 1, 3, 2. So if you add those up, that's 2, 6, 3. And if we look under the sum of the false negatives, it's 2, 6, 3. See where these numbers are coming from? So then what's the next step? You compute the learning gradient. The learning gradient is the sum of the false negatives minus the sum of the false positives. So 2 minus 1 is 1, and 6 minus 2 is 4, and 3 minus 4 is minus 1. So now you have the learning gradient, okay? And then it's like, okay, well, what's our learning delta? You multiply each component of the learning gradient, 1, 4 minus 1, by 0.22. That's our learning rate. How do I know that's my learning rate? Because I entered it right here as the learning rate. Okay, and so now my learning delta is 1 times 0.22, that's 0.22, 4 times 0.22, that's 0.88, and minus 1 times 0.22, that's minus 0.22. So then you take this learning delta and you add it to the original weights that you had. What was our original weights? Well, our original weights were Come on. -301. -301. Okay, so -3 plus 0.22 is -2.78. Okay, this was a 0, right? So, sorry, was it a 0? What was it? My memory. It was a 0. So you add that to 0, added to 0.88 gives you 0.88. And this one was a 1, so you add minus 0.22 to a 1 and you get 0.78. These are our new weights. And so what do you do with those new weights? Well, you feed those new weights, you carry them over to the next step in the process. So now our weights, well, I don't have them written down here up at the top, but those weights are these weights right here. And if you want to plot things in a slope-intercept equation, I showed you how to compute that, how to rearrange your equations to be in the slope-intercept form. So this is the line that you get, right? It crosses the x2 at 3.5, and you can see that I'm crossing at about 3.5 here. There's no good plotting or graphing built into. There's no good XY graphing that I could find that could take these values and put them into a plot. So I had to kind of cheat and do some work. But basically, except in the case where your slope is infinite, giving you a vertical line, this will fairly well approximate where the decision surface should fall. And so you see now, these two guys are properly classified. They generate 1s, and they are correct. These three guys still generate 0s, which is correct. The only one that's wrong now is 2, 4, right? That's our fourth input. It generates a 1. It's above the decision surface, but that's not correct. It's a false positive because it generated a positive of 1 when it shouldn't have. Okay. So what does this thing do? Well, it shows that if you start with the values that I have here, the values we talked about, -3 for weight 0, in other words, a threshold of 3, and a 0 for weight 1, and a 1 for weight 2, and a learning rate of 0.22, what happens is if you move out over time, these things listed step 1, step 2, step 3. Basically what I've done is I've taken the loop and I've unwound it so you can see the calculations at each pass through the loop, okay? And so here's where the decision surface is. It's way below on step 3, and then it moves to here on step 4, and then it moves to here on step 5, still way too low, and then it moves to here on step 6. And you'll notice something that happens after step 6. You'll notice that once we finish with step 6, we've got this decision surface here. These two guys will generate a positive. All of these will generate a negative. And so after step 7, nothing changes because all of the outputs are correct. And so if you look at the decision surface, 0.2851, blah, 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 well, it never changes. It's stabilized at 0.7. So it reached a stable decision surface after 6 steps. In the 7th step, everything is correct. Okay. All right. Let me switch over one moment and look at the chat. Again, I have to stop screen sharing for that. Why exactly is our threshold 3? Because we just decided to make it that, right? Remember, we set, if you look at the initial weights that we have, that's where the decision surface comes out to be. It's a straight line at x2 equals 3. But that was just random, okay? It was just random. But let's now let's put what I've said to the test. I said that you could start with any weights and learning rate, and you should still get the same answer. Well, I didn't say you'd get the same answer. I said you would get a valid answer. So let me be very careful here. So what happens if we do something real simple? We're going to keep our weights, our threshold at 3, so -3 for weight 0. We're going to keep weight 1 at 0, which means we're ignoring our x1 input and just looking at our x2. We'll keep our weight 2 at 1, right? So we'll start with exactly the same decision surface, which is a horizontal line at x2 equals 3. But I'm going to change my learning rate. Instead of being 0.22, I'm going to make my learning rate what did I set it to? 0.1, I think is what I did in this example. So now 0.1. What happens? It looks like the graph, the little lines changed, right? And let's look. Last time I stabilized after 7 passes through the loop. 4, 5, 6, 7, and I was stable. I'm not stable now. I'm still getting some answers that are wrong, right? Oh, is that bad? Well, step 8, step 9. After step 9, however, if I look at steps 10 and beyond, everything is correct. Once everything is correct, nothing changes. Now, this line is not exactly the same line that we had before. It shifted a little bit, but it's still a line that separates the 4 points in class 0 from the 2 points in class 1. Okay, so it still worked. It gave you a decision surface that is oriented slightly differently, but it still separates the two classes. Is one decision surface better than the other? No. It still moved the decision surface around until it found one that was that separated the two classes. There are, in general, an infinite number of decision surfaces that are correct. There are also, of course, an infinite number of decision surfaces that are incorrect. So let's try going back to let's try doing something here. As we've seen, as we understand now, if you set W1 to 0, that means ignore the X1 input. So this ignores the X1 input, and because I have a 1 on weight 2, it fully utilizes the X2 input. Let's swap that. Let's say that I'm going to pay attention to X1 and I'm not going to pay attention to X2. Well, what happens after that? Now, the one problem you have is the line here is drawn incorrectly. So you might say, wait a second, this line is wrong. Yes, graphically this line is wrong because I couldn't make it so that it could draw vertical lines. But this is actually and you can see the problem is, see this, the slope of the line is infinite, which is why I'm getting a divide by 0 error. But basically there's a line right here, okay, where I have is basically right here It's where the vertical line would be, and it separates these guys from these guys. So when we begin, there's no work to be done, because by random chance, it just so happens that everything is correct. So you can luck out and have parameters set so that there's no learning that needs to be done. It's just verification. Yeah, it knows everything. Now, I can make that happen when I only have 2 inputs and I play around with the weights, but in general, that's not going to be that's not going to be the case, right? Okay, so that was 3, 1. How about if I come here and I set this to 0.05? Okay, now we find that, and I'm going to set the learning rate to 0.22, which is what I have in my notes. And you would see that on this one, it will stabilize, I think, after 9 iterations. So it's still moving along. You can see I'm still getting, I can't point at it with my finger, but I can with this. I'm still occasionally getting inputs that are incorrect, but after 9 passes, from the 10th pass onwards, everything is correct. And again, you notice these numbers are different each time. You get a slightly different decision surface each time, but that's fine. It learned. So let's get really aggressive here. Let's change this to a -1, and let's say ignore both of the inputs. You might say, Mike, if I'm going to ignore both of the inputs, there's no way this thing is ever going to learn anything. Well, what happens is that it will learn. Let's see, it classifies everything correctly, I believe in this case, after 14 iterations. Why? Because, yes, it's ignoring things, the X1 and the X2 on the very first pass, but then the decision surface changes and it's not ignoring them after that. And you can see that it's learning, right? It's learning, and it looks like here, everything is correctly classified. I guess actually after quickly, after only 4 steps, everything is correctly classified. How about if I just say I want to be pig-headed and I want to set everything to 0? My threshold 0, my weights are 0. Now my learning rate can't be 0. Your learning rate has to be some positive value or you'll never move. The learning rate says how far I'm going to move. If you set that to 0, you're never moving your decision surface. But as long as the learning rate's non-zero and you've got any kind of an input, it'll still work. This one takes a long time. This takes a long time, a long time, a long time. Yep, this is how many of these loops that I unwound for you guys, right? A long, long, long time. But after step 40, it stabilized and got everything correct. So even when I started with everything being 0, except the learning rate. The learning rate can't be 0. Then it works. So essentially, like I said, and I haven't given you a formal mathematical proof, but I've gone through half a dozen or more examples and showed you it doesn't matter what you set your threshold to or your weights to. As long as you've got a positive learning rate, it's going to learn. Okay? Normally, what we do is we set the threshold and the weights randomly to begin with. Why? Well, we don't know what the right answer should be, and setting everything, as I showed you, setting everything to 0 can sometimes cause it to take a long, long time. So set them randomly. But you don't have to. You can set them to your favorite numbers if you want to, and it'll still work. I think that's pretty cool. Okay. Are there any questions about that? Any questions about that? Now, I know we finished the section of the class that dealt with philosophy and philosophical problems, but I want to ask a philosophical question. How do we know that the perceptron has learned what we want it to learn? With our little problem that we've been playing with, let me put it back up momentarily. With this little problem, just looking at it, you know that 4-1 should be yellow and 4-2 should be yellow, and probably 4-3 should be yellow. But and I would say you probably would suspect that 4-4 would be yellow. But what about these two guys, 4-3? What about 4-3? I could probably draw a line. It would depend on the exact spacing, but I might be able to draw a line where this guy was gray. You might be able to get a straight line. You might not. The way this is drawn, you might not be able to get a straight line that would be able to include this guy in the positive set and not this guy, and pass in such a way that that 4-3 or actually 3-4 would be great. The question is just looking at it, the fact that I'm talking about this means that it's not really obvious what 3-4 should be. It's gotten too far away from the examples that we have here, right? I can tell you that 4-4 ought to be yellow, and 4-1 should be yellow. Should this thing here be yellow or gray? Well, if it's yellow, you can see that the problem's you're not going to be able to draw a line to separate the two classes. So then you would have a problem that's not perceptron learnable. Assuming the problem really is perceptron learnable, well, this guy's going to have to be in the gray class, in the don't fire class. But what's the real problem that we're modeling? What is the real shape of these sets? Because these are just sample points, right? In two classes or two sets that we're trying to identify. I don't know. I just have training data here. And from this training data, I'm moving a decision surface to separate the points that I do know about. I don't know about future points. So normally after you train a network, what you do is you turn around and you test it against real world data to see that it's never seen before, to see if it recognizes it. And so going back to that old video that we saw from the 1960s that was in black and white, where you're trying to tell males from females, well, you train on a lot of pictures of women and you train on a lot of pictures of guys, and once it seems like it can recognize the difference between men and women, then you show it pictures it's never seen before. And, will it be able to identify every single woman and identify every single man? Maybe not. Maybe it'll only be able to identify most men and most women, right? We don't know. And that's a problem. There's an old And this applies not just to perceptrons, this applies to neural networks in general. You never really know what it learned. And there's a wonderful story that may or may not be apocryphal, right? When you say a story is apocryphal, well, it's a story that's gone around, but no one really knows if it's true or not. But there's a story that's gone around AI circles for many decades, and it involves a project that the government was using early neural networks, probably perceptrons, to try to look at aerial photos and find out whether or not there were tanks in the photos, right? Because if you think about satellite imagery, or you think about spy plane footage, you have lots and lots and lots of images. And, you know, it would be nice if a human didn't have to look at every image. So if you could have an algorithm look at the images. And so one of the things that they tried was to train a neural network to be able to recognize tanks. So how are you going to do this? Well, I need data. So they went out and they had a bunch of tanks and they had a forest, and they took a bunch of photos of the forest when the tanks weren't there. And then the next day they brought in a bunch of tanks, and you know, they had tanks out in the open, and they had tanks partially behind trees, and they had tanks where maybe only you could see the turret sticking out or whatever. So they had all of these photos that they took on one day of just forest photos. And then on the next day, they went and they took all of these pictures, same forest, right, but tanks in partially hidden in different ways. Then they trained the network. And dang, they were able to get 100% or very near recognition, where the neural network would say, this picture has tanks in it, this picture doesn't have tanks in it. And the scientists were like elated, right? It was working far better than they expected that it would work. But to make sure that it was really working properly, they went out and they took another series of photos that the algorithm had never been trained on and had never seen before. And when they gave the pictures to the new pictures to the algorithm, to the perceptron, it totally screwed up. It was just like it was randomly guessing. It couldn't tell the difference between the photos with tanks and the photos without tanks. It hadn't learned to recognize tanks. What it turned out that it had learned to recognize was that the day that they took the photos of the forest without the tanks was a sunny day, and the day that they took the photos in the forest with the tanks was a cloudy day. And the perceptron had learned to recognize sunny day pictures from cloudy day pictures. So the answer is we never really know what the network actually learned, and that is kind of scary. Let's see, one of our Jonathans is saying, I've also heard of a model meant to diagnose based on X-ray images. They found out it was using a watermark that identified the machine that took the images. Some X-rays are used more for clinics versus hospitals. Yeah, I mean, you have to be very careful that there's not some bias in your data, because the perceptron doesn't know that you're trying to teach it about tanks, or trees or anything. It's just, what's the difference? What are the differences between these things? And that difference could be anything. It could be something that a human would never think about. So that's a pretty funny story. Like I said, it's gone around for years and years. Whether or not it's truly true, I don't know. Okay, next up. Before we talk about multi-layer perceptrons, let's talk for a moment about single-layer multi-perceptron networks. So single layer, we'll have a single layer, but we will have multiple perceptrons. Now, I've said the single perceptron learning algorithm will work for these, but I haven't really explained why. So let's look at an example. So here is a single layer perceptron, right? Single layer neural network, and you can see it's got inputs, right? And those inputs have weights. And to make it clear, I've drawn all of the weights for one perceptron in green, and I've drawn all of the weights and everything else for the other perceptron in blue. What's very important to understand is this perceptron can in no way communicate with this perceptron. They don't share anything in common. They don't share weights in common. There's no feedback mechanism between them. They essentially function in isolation. Now, you might say, well, okay, but could it be useful? Well, you could imagine a single layer multi-perceptron network that might be able to do things like determine short males and tall males and short females and tall females. So 4 categorizations, right? But the way it's working internally is there is one perceptron that's asking the male-female problem, and there's another perceptron that's asking the tall-short problem. So, yeah, you can think about this thing as generating 4 different outputs, short male, tall male, short female, tall female. And it is, it's generating 4 output classifications, but really both perceptrons work totally in isolation. So the perceptron learning rule that we've already described that works on single perceptrons is perfectly capable of being applied to this problem. It's just 2 different problems where you're training this one and you're training this one, but you're training them separately. Both of them are being trained by the perceptron learning rule. So does that make sense? Does that make sense? It makes sense to Jonathan Walters. Does it make sense to anybody else? Okay. So again, you can have multiple outputs, but that doesn't change the model at all, as long as everything's in a single layer, and you can still use the perceptron learning rule. Now, long ago, we talked about the fact of early on, back in the McCullough-Pitts days, when they were first generating McCullough-Pitts neurons, that they had claimed that you could implement essentially all logical operations could be implemented by neural networks. Okay, can we prove that? It's very easy proof. I'll show it to you right now. It is all you need to build any logical operation are 3 gates, 2 if you want to use AND and OR, but 3 gates, AND, OR, and NOT. And here they are. If you have, and again, in this case, we are assuming, in general, your inputs to perceptron can be any values you want. But if we're talking about logic gates, then we're going to talk about our inputs being either 1 or 0, and our outputs being either 1 or 0. So here is an AND, okay? So basically what this is you've got 2 inputs, they're equally weighted with 1s, right? And you've got a threshold of 1.5. Well, if you do it as a weight, it's negative 1.5, right? So if x1 is a 1 and x2 is a 1, then this is 1 times 1 is 1 plus 1 times 1 is 1. So now you got 2, and then you add to that 2 minus 1.5. That gives you a 0.5. That 0.5 is greater than 0, so you fire. So if this is a 1 and this is a 1, it fires. If either or both of these guys are 0, right? If either of these are 0, you're going to get a 1 plus a minus 1.5, which is going to give you a minus 0.5. That's not going to trip it. And if both of these are 0, you're going to get a minus 1.5 plus 0 plus 0, so a minus 1.5, and that's not bigger than or equal to 0, so it's not going to trip it. So this is an AND. Does everyone see? This is an AND gate. Functions exactly like an AND gate. It is an AND gate. How about an OR? Can we build an OR, a perceptron OR? Sure you can. If these are both 1 again, but we've changed our threshold from being 1.5 to being 0.5. Again, if you're adding it as a weight, it'll be negative 0.5. But now if either of these guys are on, or if both of them are on, if either are on, you'll get a 1. All right, let's say this was on. So here's a 1. Let's say this one's a 0. So a 1 plus 0 is a 1. Subtract 0.5 from it, you got 0.5. That's greater than 0, so you fire. So if this guy's a 1, we fire. If this guy's a 1 and this guy's a 0. Let's say this guy's a 0 and this guy's a 1. You're still going to get 0.5 and it's going to fire. Let's say that they are both 1. Okay, well now you're going to get a 2, subtract a 0.5 from it, so you got a 1.5. That's greater than 0, so you fire. How about if both of these are 0? Well, this is a 0 and this is a 0. 0 plus 0 is 0, plus minus 0.5 gives you minus 0.5. Minus 0.5 is not greater than or equal to 0, so you don't fire. So the only time the OR doesn't fire is when both of these are 0. Other times it fires. So that's perfectly an AND. That's perfectly an OR. How about a NOT? It's easy to build a NOT. Put your threshold at minus 0.5. Okay. So when you put it on a weight, right, you have to flip the sign, so it's 0.5, and let the weight here be a minus 1. So if I enter a 1, what will I have? A 1 times a minus 1, I'll have a minus 1, right? So I entered a 1, a minus 1, plus a 0.5, right, is a minus 0.5. So this is not above 0. It's not equal or above 0. So when this is a 1, this generates a 0. How about when this is a 0? Well, when this is a 0, you have 0 plus 0.5. That's greater than 0, so you fire. So when this is a 1, this is a 0. And when this is a 0, this is a 1. I've proven and or and not. So given and or and not, I could generate any logical circuit that you could build. I could build out of these little perceptrons, right? So basically, inputs, weighted inputs with a summation and a threshold comparator is all you need to build any of the logical gates and or not. So because this is true, you could build any kind of computer circuitry completely out of perceptrons. But wait a second. You said, Michael, that that a two-input perceptron couldn't solve the XOR problem or the equal problem. Well, a single perceptron can't, right? But if you have multiple logic gates, you can build something like this. This is a multi-layer perceptron neural network. So, and I'm creating an XOR solver here. This guy has, instead of just one layer, it has two layers. It has a hidden layer and an output layer. So it's got your inputs and your outputs just like before, but now it's got another level of perceptrons in the middle. The perceptron learning rule cannot train this thing, but I can set the weights by hand to make it do anything I want it to do. And in this case, I've set it up so that it is an XOR. I had to hand code it. Now, you might say, I don't see that this does anything, Michael. Yeah, well, there are actually three perceptrons here. There's the green perceptron, the blue perceptron, and the black perceptron. I use different colors for the lines and for the text. Essentially, what the green perceptron does, and I'll scroll down here a little bit so you can see it. What the green perceptron does is it generates a 0 except when x1 is a 1 and x2 is a 0. In that one case, when x1 is a 1 and x2 is a 0, it generates a 1. Let's see if we can trace that through Mr. Green here. So when x1 is a 1 and x2 is a 0, right? Well, this is a -1 weight, so x2 is a 0, so that's going to be off. It's not going to do anything. This is a 1, so 1 times 1 is 1. So the 0 from here plus the 1 from here plus the -0.5 is going to give you a 0.5, and it's going to fire, right? With any other, with 0, 0, 1, 1, or 0, 1, it's going to always, the summation here, I'm giving you what the summations are, they always fall below 0, so it produces a 0 output. So Mr. Green perceptron is going to produce a 1 only in the case when x1 is a 1 and x2 is a 0. And we can make Mr. Blue be the evil version of Mr. Green, the exact opposite of Mr. Green. And so Mr. Blue will fire only when x1 is 0 and x2 is 1. It'll be a 0.5 in that case, and it'll fire. In all other cases, it will fail to fire. I strongly encourage you to go through these numbers and prove to yourself that I'm being honest with you here, rather than just go, no, he wrote some numbers, they're right. Okay, I want you to think through the problem. So we've got Mr. Green coming in, and we've got Mr. Blue coming in. Again, Mr. Green can only produce a 1. In other words, you can only get a 1 here at this level through Mr. Green when it's 1, 0. And you can only get a 1 here when it's 0, 1. And those go into Mr. Black, and Mr. Black is set up so that if you get a 0, 1 or a 1, 0, Mr. Black will generate a 1. If green and blue are both 0, then you get an output of 0. And what if Mr. Green and Mr. Blue are both 1? That cannot occur because the input conditions for green are exactly the opposite of the input conditions for blue. So there is no way that green and blue can be firing at the same time. And that's why I grayed out and put non-applicable on this third row, because it just can't happen. There's no way that the black node, the black neuron, can get a 1 and a 1 on its inputs, because one of the inputs is Mr. Green and the other input is Mr. Blue. And when Mr. Green generates a 1, we know that Mr. Blue is off, generating a 0. And when Mr. Blue is generating a 1, we know that Mr. Green is off, is generating a 0. Does that make sense? Questions? I'll stop sharing so that I can look at the chat. Does that make sense, my friends? Comments, questions? Yep, yepers, makes sense, goods. Okay, awesomeness. All right. So what have we done here, right? What have Mike wrought? Well, I've shown you that we've done a bunch of things here. to finish off perceptrons. I've shown you that it doesn't matter what your weights are and what your initial weights and initial threshold are. It makes no difference whatsoever. The only effect is it could take you a little longer or a little shorter to reach the answer, right? We've gone through and shown that, again, we reiterated something we talked about at the end of lecture last time, which is that perceptrons are just moving the decision surface. That's all they're doing, trying to separate two input classes. And if the two classes are linearly separable, and that simply means that if you've got two inputs, x1 and x2, you can draw a line between the two classes. If you can do that, then it's linearly separable. It's not always a line, though, because if you've got only one input, your inputs are just numbers, and then the decision surface is a point. But it's the same thing. You've got to be able to put a point between one class and the other. If they're interwoven classes, so there's no decision point, the perceptron can't solve it. If you've got a three-dimensional input, then it's got to be possible to separate those two classes by some kind of a plane, to use some two-dimensional plane and some orientation. If you can't separate three-dimensional inputs by a flat plane, it's unlearnable. Once you get above 3, when you get to 4, 5, 6, 100 inputs, there's no way you know. So it gets back to this thing of, okay, I'm running my learning algorithm, and it's ran for 10,000 cycles. Do I quit? Do I hit, the escape button? Well, the answer is you don't know, because if the problem really is perceptron learnable, then it will eventually find the decision surface. But if there is no decision surface, it can look forever and not find it because it doesn't exist. So it's that same kind of a halting problem type problem that we talk about in theory of computing. So one other little thing that I wanted to show before I close the book on perceptrons and move beyond them is I wanted to say one more little thing. You might have noticed my solution here for XOR uses 3 handcrafted perceptrons, Mr. Green, Mr. Blue, and Mr. Black. I introduced the XOR problem this way because I wanted to show you the simplest solution to the XOR that I could think of rather than a more complicated one. But you might have noticed that what I didn't do is, in this example, I did not use the and, or, and not that I had just created immediately above. Why didn't I? Well, I could have used and, or, and not. It would have been a little bit more complicated looking circuit. And here I show you that. What is an XOR written with and, or, not? So one way of writing an XOR that I kind of like is to say an XOR is X1 or X2 and not both X1 and X2. I'm using an extra little widget, but it completely follows the English of how you describe an XOR. X1 or X2 and not both X1 and X2. And you can get rid of a gate if you do it like this. Well, you still have knots, but another, I guess I should say, not a simpler way, I guess I should say another way that people do this is with an and where you not one of the inputs, and then another and where you not one of the other inputs, and then you OR those together. If this is an and, which is normally considered an atomic gate, then it just needs 2 NANDs and an OR rather than 2 ANDs, an OR, and a NOT. So if you consider NOT and a NAND as an atomic gate, and double E's, nor electrical engineers normally do, then this is a little more efficient because it's 2 NANDs and an OR rather than an OR, 2 ANDs, and a NOT. But anyway, if we take this X2 kind of way of looking at an XOR circuit, you can show the same thing implemented with perceptrons. Here's our NOT. If you go back and you look at, we had to find a NOT, it had a -1 and a 0.5 as the threshold. And here's an AND, it had a 1 and a 1 and a -1.5. And here's an OR, it had a 1 and a 1 and a -0.5. Here's an AND, a 1 and a 1 and a -1.5, so it's the same thing as this one. This NOT's the same thing as this one. So this is, if you wanted to build it like in exactly the same way that we would have built it using ANDs, ORs, and NOTs, you could just use the perceptron for AND, the perceptron for OR, and the perceptron for NOT, and transliterate it, and you would get an exclusive OR. I just didn't start this way. I wanted to show you can do it this way, but I didn't want to start this way because, quite frankly, that's a lot more complicated than my pretty little handcrafted XOR that I built out of 3 perceptrons. So you can frequently get away with fewer perceptrons if you hand code the thing rather than going back to the perceptron for NOT, the perceptron for AND, and the perceptron for OR. But you can always go back to them. They're always there. And because they're there, you know that you can build any kind of electronic circuit, any kind of logic circuit, adders, comparators, you name it, out of perceptrons because you got your AND, your OR, and your NOT. Any questions? Any more final questions about perceptrons? Any more final questions about perceptrons? Okay, so we now want to move beyond perceptrons, and we want to start focusing on multi-layer neural networks. But before we can talk about multi-layer neural networks, we have to talk about what does a neuron in a multi-layer neural network look like. They are very similar to perceptrons, but they are not identical to perceptrons. They're very similar, but they're not identical. So the first thing we have to do is we have to learn, okay, how does a perceptron in a modern neural network, or how does a neuron in a modern neural network differ from a perceptron neuron, a perceptron? The biggest difference is that the output of a perceptron is a 0 or a 1 and nothing in between. The perceptron, an output of a perceptron is a 0 or a 1 and nothing in between. The output of a neuron in a modern neural network is a continuous function that often varies from -1 to +1. It can have other values, but the important thing is it's a continuous function. It's not a discontinuous step function. It's a continuous function, and because it's a continuous function, it can be differentiated, where a step function can't be. So that's the biggest difference between a perceptron model of a neuron and the model of a neuron that we now use today, is that the output of a modern neuron can be a continuous function, where the output of a perceptron is discontinuous. It's a step function. It's either 1 or 0. So that's the big difference. Well, how is that big difference implemented? Let me move forward so that I can show you that. So this continuous function neuron is kind of the basis of everything that we're going to do. So let me come back here and go into share screen mode. Now, the material that I'm going to be talking about here is from an online book called Neural Networks and Deep Learning by Michael Nelson. It was first published 5 years ago in 2015. It's available at neuralnetworksanddeeplearning.com. The book is completely free. It's online. And it's rapidly become sort of the standard text. So the best text that you can get in this area is absolutely completely free. We're going to be looking basically at chapters 1 and 2. That's all we're going to look at. I think it's like got 8 or 9 chapters in it, but we're only going to look at chapters 1 and 2, which get you started, give you the basics of how neural networks are built. So between that and some YouTube videos, that's where this material is coming from. Okay. So the big differences between perceptrons and modern neural networks, the big architectural differences are that modern neural networks, the model of the neuron has been changed slightly so that it generates a continuous output function. And also the architecture now has multiple levels in it rather than a single layer, multiple layers or levels. And when you've got lots of these layers, you then call it a deep neural network. Deep just means there are a lot of levels. How many levels do you need to have for you to call it a deep neural network? I don't know. It depends. So that's the big difference. There's also going to be some differences in for different kinds of neural networks in the way that they are how the inputs are wired into the neurons. But we're not going to really talk about that. We're going to talk about, or most of the time, we're going to talk about what are called fully connected neural networks. And these fully connected neural networks use the same model that we've started building with perceptrons. So let's look and see what do I mean by that the output is continuous. Well, with the perceptron, the output is either 0 or 1. So it is 0 if you think about this axis as the output, and you think about this axis as the input, the weighted sum of the inputs. Well, the weighted sum of the inputs, once they reach 0, you have this discontinuity that switches the output to 1. So the output is either 0 or 1, and you have this discontinuity here. So it's either 0 or 1, nothing in between. It instantaneously jumps at 0. So you can be, negative 0.9999999, or that's not right. You can be negative 0.9999999, and or I guess I should say 0.000000001, right? And you'll still be generating a 0, but the moment the sum switches from minus 0.00001 to 0, your output immediately switches to a 1. Okay? With a logistic neuron, you get a smooth kind of an S-curve. And if we drew this out further, this would be almost completely 0, and this would be almost completely 1. It never absolutely reaches 1, and it never is absolutely at 0, but these asymptotically approach. This asymptotically approaches 0 as you go this way, and this asymptotically approaches 1 as you go this way. So, but when you're near, when the sum of your inputs is near 0, you get this smooth transition between the 0 state and the 1 state. Okay, and so this function is differentiable because of that. There are different functions that you can use for the output. The one that we will talk about is called the sigmoidal function, the sigmoid, and these are called sigmoid neurons or sigmoidal neurons. Sometimes they're called logistic neurons. But the only difference is that you got a real valued output between 0 and 1 inclusive instead of a step function that's either 0 or 1. So that's the only difference you have here. Now, what does a logistic neuron look like, or a sigmoidal neuron look like? You might look at this and you might say, well, that's perceptron, Mike. Yeah, it's really, really super close to perceptron. There are some slight differences. Like originally when we introduced the perceptron, we had a threshold that was kept separately. Well, now we have something called a bias. It's essentially exactly the same thing as a threshold, okay? But we've got a bias, okay? And we still have a bunch of inputs, and each of those inputs has a weight. You still have a summation unit that computes the weighted sum of the inputs plus the bias. So this part of it works completely the same. And the sum of the inputs is called Z. But Z is not the output of the neuron. In a perceptron, you would compare Z to a threshold comparator. And if it was equal to a threshold or greater, you would return a 1. And if it was less than the threshold, you would return a 0. But we don't do that. Instead, we place Z into some function, sigma, if it's a sigmoidal, right? And it generates a Y value. This Y value is not necessarily 0 or 1. It's any value between 0 and 1, okay? So you're getting a real value in the case of a logistics neuron or in the case of a sigmoidal neuron between 0 and 1. So again, its operation is very similar. Compute the weighted sum of all of the inputs, adding in a bias. Take that weighted sum of the inputs plus the bias, call it Z, throw it into a sigmoid function. The output of that sigmoid function becomes the output of our neuron. Okay. So we can mathematically describe what's going on is to say that Y, which is the output of the neuron, is your sigmoid function taking in Z, where Z is the weighted sum. Here are the weights, here are the inputs, the weighted sum of the inputs over all of your inputs, right, plus your bias. That is Z, which we plugged in here to our sigmoid function. Here I've written things in kind of a computer science-y like notation where I'm showing the actual loop. That's I goes from 1 to n, and this is Wi times x sub I, and you sum up all of those, then you add in the bias. That gives you your Z. You plug the Z into the sigmoid. A more mathematical way of looking at what we're doing here, it's exactly the same thing. It's just, this is kind of looking at it in a format that computer scientists tend to look at these things in. This is looking at it in the form that a mathematician tends to look at it in. It's the Y is the sigmoid function applied to everything in these parentheses. Well, what's everything in these parentheses? It's z. Well, what is z? You can express z as the weight vector times the input vector plus the bias. The weight vector times the input vector will give you a scalar, will give you a number, right, plus b. These two things are saying exactly the same thing. So how do you compute w times x? Well, it's w0 times x0, right, plus w1 times x1 plus, it's exactly, this just spells out how you do this multiplication here. And once you get the result, you then add in b. Well, after I get this result, I add in b. So this gives me z. I didn't call it z here, but this gives me z, and I plug z into the sigmoid function. Questions at this point? Don't see a lot of questions, so I'll continue to move forward. So everything should make sense at this point, except, Mike, you haven't told me what this sigmoidal thingy is. It's like, you told me everything about what goes into it. I now know what the z is. The z is the weighted sum of the inputs plus the bias. It's basically everything that, it's basically everything that our old perceptron did, the weighted sum of the inputs plus the bias, that's z. But what is this friggin' sigma that you've got here? Sigma is defined as 1 over 1 plus e to the minus z. At this point, I can't see you guys, but I see most of in my mind's eye, I see most of my computer scientists regurgitating and trying to swallow it before actually spewing barf all over the computer screen. Because you look at this and you go, we don't have anything like this in computer science. What is this E thing? And even I know, okay. But really, it's not bad. It's fairly easy to compute, right? And it is a function that's frequently used in engineering and the natural sciences. E is the base of the natural logarithm, okay? So we deal with logarithmic functions all the time in computer science and analysis of algorithms, for example. But we use base 2. Well, why? Because everything we do is digital. It's either 0 or 1. So everything that we do is either raising something, 2 to whatever power, or if it's logarithmic, it's base 2. We don't use base E. But like I said, base E comes from the natural sciences. So if we look at this, what is E? Well, E is a constant. That constant can be computed. The number of the constant is 2.71828. It's Euler's number, right? And how can you compute this weird number that is E, that is the base of the natural logarithm, and why is it that? Well, it's really 1 over n factorial summed up from 0 to infinity, right? So it's basically it's the sum of 1 over n factorial. So 1 over 1, which is 1, plus 1 over 1, which is now we got 2, plus 1 over 2, so that's 0.5, plus 1 over 6, plus 1 over 6 times 4, 24, plus blah, 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 blah. It's just the infinite sum as n goes from 0 to infinity of 1 over n factorial. That's all it is, okay? That gives you E. And also, if you want to plot y over 1 over x, right, you get this pretty little curve here. E is all of this blue shaded region, this light blue shaded region, or turquoise, from 1 to E. The area under this curve is one square unit, okay? So putting everything together, what we've just talked about, y is 1 over 1 plus e to the z. Well, what is z? Or to the minus z? Well, what is minus z? It's minus the w times x vectors plus b. So that's what it is. And if you don't like looking at it like this, you can look at it more like what you would write in a computer language, right? Now you'd have to split this out into a loop that would do the computation, but it's 1 over the quantity, 1 plus usually e to the whatever power. There's usually a function for that, exp, and then what's the power? Well, it's the z value, and we've already talked about how to calculate the z value. So it's e to the minus z. So I've got a little minus here, and here's my z being calculated. At this point, you're probably going, my head hurts. Well, the nice thing about learning online is you can go over to your liquor cabinet and make yourself a nice tall drink now and sip on that while we think about this, right? But it's not that bad. It's not that bad. And it's actually, so you might say, okay, I've seen E in other classes, so I'm not too concerned that you introduced it here, Mike. And I've seen the sigmoid function before. Maybe you have in a math class. So, okay, that's not too crazy. But why? Why did a computer scientist somewhere decide to define these new kind of neurons this way? Why are you using a sigmoidal function here? There are lots of functions that could be used. The first one, and it's still quite popular, is the sigmoid function. Why the sigmoid function? Well, because the sigmoid function is essentially a continuous version of what we were already using in perceptrons, okay? Perceptron outputs are either 0 or 1, but if you want to be able to differentiate, which we're going to have to do, a function, it can't be a discontinuous function. So the sigmoid function does the same thing. It starts out very, very, very near 0 and stays very, very, very near 0 until you get close to the threshold, to the 0 threshold, and then it rises smoothly towards 1. And then as you get away from your threshold and you get to bigger numbers, it stays pretty much at 1. So really, the only area that the sigmoid is different is right around the 0 threshold, where instead of a discontinuous, it's a smoothly continuous function. So we're using the sigmoid because it's very close to the step function we were already using in perceptrons. Now, what do you mean it's very close? This looks like an S, and this looks like a step function, a step. Well, what I'm saying here is when you're greater than your 0 threshold, your output on a perceptron is always 1. And when you're smaller than your threshold, your output's always 0. If we ignore the area right around our threshold, well, if you're much bigger than your 0 threshold, then you're pretty much at 1. And if you're much smaller than your 0 threshold, you're pretty much at 0. So away from this area right around your threshold, a perceptron is generating a 1 and a sigmoidal neuron is generating a 1. And if you're very far away from your threshold on the other side, you're much smaller than your threshold, your perceptron is generating a 0 and your sigmoidal neuron is generating a 0. So their behavior is very similar, except that the sigmoidal is continuous, whereas the perceptron is discontinuous. We can see mathematically that what I'm claiming here is true, that the sigmoid behaves a lot like the the step function. And let's think about this in a couple of different ways. Let's say that the weighted sum of your inputs is plus the bias is a large positive number. The sum of your inputs is a large positive number, which means that we're far above our threshold. Well, if that's the case, we would expect that our output from our sigmoid is 1 or very near 1, and we would expect that the output from we already know our output from our perceptron would be 1. So why is this true? Well, what is e to the minus z? Well, e to the minus z is 1 over e to the z. Well, what is e to the z? Well, it's 1 over e is just 2.781 blah, 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 blah. And we said that z is going to be a large positive number. So e to the minus z, another way of writing that is 1 over e to the z, right? The minus is just 1 over e to the z, right? And so we said that if z is a large positive number, we've got a number bigger than 1, 2.7, it's almost 3 as our base, and we're raising that to a large positive value. Well, what is a number greater than 1 raised to a large positive value? It's a very large positive number, right? So what is 1 over a very large positive number? It's about 0. Okay, so now then we know that if we've got a large positive number for z, e to the minus z is going to be about 0. So let's plug in a 0 for e to the minus z here. So now we have 1 over 1 plus 0, and 1 over 1 plus 0 is 1. So yes, when your z is a large positive number, and you plug that z into the equation here for the sigmoid, it's about 1. Let's look at on the other hand. If z is a large negative number, so now then we're far below our threshold of 0. So z is a large negative number. Well, in this case, e to the minus z is e to the minus a large negative number. Minus a large negative number is going to be a large positive number. Negative, negative cancels, right? So now we have e to a large positive number. E is about 3, a little less, 2.718 to a large positive number is going to be a very large positive number. And so now then you can plug in this very large positive number for e to the minus z, and we see that you've got 1 over 1 plus e to the minus z. Well, that's a very large positive number. So 1 over 1 plus a very large positive number is going to be a very large 1 over a very large positive number. The 1 doesn't matter. So basically you got 0. 1 over a very large positive number is close enough to 0 to say it's 0. So for large positive numbers, numbers that are for weighted sums plus biases of your inputs that are large positive numbers, you get a 1 out of the sigmoid. For large negative numbers, weighted sums of the inputs plus the bias that are far below our input, you basically get a 0. So this is this is why the function generates a shape like this, and really it's identical. It's not identical. It's very similar. It has very similar characteristics to our perceptron. The only difference being that the perceptron is a step function that's discontinuous, and here with the sigmoidal, we've now gotten rid of this discontinuity, and there's a smooth transition between very nearly 0 and very nearly 1, and this occurs right around our threshold. Does that make some sense? Does that make some sense? Okay. Let me stop this and look at the comments here. Yes, 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 yes. Drink. I don't have at the moment, but I'm out. I'm out. Well, sorry guys. Poor planning, you know, is not my fault. So you should be taking advantage of the positives of having lectures online. But seriously, are there any problems with this? Do you see what I'm saying? Basically, it looks weird to a computer scientist, the sigmoid function. Why did we choose it? We chose it because it acts pretty much in the same way that the perceptron output acts, except it's a continuous function, and we're going to need that to be able to differentiate. And so you get a smooth transition between the 0 and the 1, rather than this discontinuous jump. It's either at 0 or it's at 1 and nothing in between. Okay. Why did they choose E? Ask our mathematician. Because the natural, the base of the natural logarithm, the natural logarithms exist all through the natural sciences. We don't see them very much because, again, there's nothing natural about computers, 0 or 1, so we use base 2. But outside of our little world of computer science, pretty much everything works on E. E is actually very, very interesting if you start reading Wikipedia about it and seeing all the places that it shows up. It's just really weird how it shows up so much in the natural world. So, okay. So let's see. So I have about 5 minutes left. Where am I going with this? Okay. Let me share my screen again. We're getting ready to talk about a 3-layer network. And this is the architecture of a network that we're going to be playing with quite a bit, and is actually very close to, you may have more nodes in your middle layer, but this is very close to the architecture that you're going to use to solve your first programming assignment. What we're going to do, and this is, and Michael Nelson's book talks you through it, what we're going to do is we're going to build a neural network that that solves the MNIST handwritten digit problem. What is MNIST? The NIST in MNIST is the National Institute of Standards and Technology, and basically the MNIST data set is a machine learning. It's like the granddaddy machine learning data set that's been around forever. One of the first uses for or application cases for neural networks was the post office. And the thing there is that if you go back to like the 60s and the 70s, you had to have a human read the addresses, and not so many years ago, you would have lots of ladies, because women always got stuck with the crap jobs. Sorry about that, women. Hopefully that's all changing. But you would have lots of women who would, there were these little machines, and there was a little hand that would like grab a letter and throw it in front of them, right? And then what would happen is the human would read the zip code and 71263, and then they would type that in, and then that letter would get sent by sorting to the next station. And so basically the zip codes would get mail to the appropriate geographical region. But so that's what would happen is a human would read the zip code, type it into a machine, and then that machine would send the letter down different little sorting tracks depending on what the human input as the number. Even though a human can, read one and process it in just a, couple of seconds, think about a human having to do that for every piece of mail, right? And this was before email, so everything went through the mail. So even paying those people not very much money, right, was very, very labor intensive. And so the post office wanted machines to be able to read handwritten digits, because if you could solve that problem, then you could dramatically decrease the cost associated with sorting mail if you could sort it automatically. And so one of the very first successful applications of neural networks were these networks that could recognize handwritten digits. Because if you could do that, then that was a huge step towards solving this problem. And in fact, this was one of the first successes in machine learning that had huge economic impact, was being able to read digits, read zip codes to be able to sort mail. So what we're going to be doing over the on Thursday is we will pick it up here, and we will begin talking about this data set and this network. And there are kind of two pieces that we've got to do. The first piece is that we've got to understand how the network works once it's been trained. Just you give me a trained network, how does it actually work? And what does the math look like, and how would you implement that in a computer? And then once we understand how it works, then we can start asking ourselves, well, how can you train it? So the first thing we're going to do is we're going to pick it up here next time, and we're going to talk about making the network actually work. And then the next thing after we know how the network works is we're going to start talking about, well, how do you train the thing? Okay. Okay. There's some questions here, but I think what I'm going to do is I think I'm going to end the lecture at this point, and I'll answer the questions after I've killed the lecture. So I will see you guys on Thursday, and we will pick it up here at that point. So, okay, so I lost my background. Crap. Okay. But anyway, Gort and Klaatu are gone. But anyway, we'll pick it up here on Thursday. See you then. Bye-bye.